Welcome to the deep dive. So our scene today, it's set near this coastal fjord, and there's this old steel factory. Well, a former steel factory.
Right, and it didn't just leave behind memories of production.
No, exactly. It left this sort of invisible, really persistent legacy. Industrial waste, contamination, and some pretty profound health issues for the workers and, well, their families too.
And our sources today, they really take us right into that history. It's alarming stuff, focusing on the heavy metal culprit, manganese.
Yeah, manganese. We're going to follow its path, basically, from the dust in the factory into people's bodies, then out into the soil, and eventually right down into the fjord.
But it's not just looking back, is it?
No, not at all. This deep dive, it's really anchored in something very current, inspired by these two students, Kesser and Steen. They've got this idea, potentially quite ingenious, actually, a nature-based solution to, well, try and clean up this toxic mess.
Which is fascinating. But before we get to the danger, the toxicity, we kind of have to start with a bit of a paradox, don't we? Manganese, Mn, it's actually essential for life.
That really surprised me when I read that. I mean, you hear heavy metal and you immediately think poison, right?
Totally understandable. But yeah, the research is clear. It's everywhere in our tissues. Acts as a critical element, a cofactor, helps enzymes do their job.
Cofactor.
Right.
So what kind of jobs?
Oh, basic metabolic functions. Processing proteins, carbs, fats. It's vital for that. And it plays a part in, well, everything from reproduction, bone formation, even regulating blood sugar.
And protecting our cells, something about mitochondria.
Yes, exactly. Protecting the mitochondria, the sort of energy centers in our cells, from oxidative damage. So it's fundamental at the right levels.
Okay, so life-sustaining, trace amounts. Okay, let's unpack this then. If it's so critical, how does it flip? How does it become this major health hazard, especially for people working in iron and steel for years?
Well, the pivot, as you call it, happens with high concentrations. That's key. And crucially, the way people are exposed.
So not eating it generally.
Not typically the main industrial risk, no. For these steel workers, the primary problem wasn't ingestion. It was long-term inhalation of this really fine dust, generated during processing, mining, handling N alloys.
Breathing it in day after day.
Exactly. That heavy chronic exposure. That's what tips the scales from essential element to toxin.
And the body just can't handle that amount coming in that way.
Yeah, it struggles, yeah. Unlike some other things, our bodies don't really have an efficient way to get rid of high levels of manganese once it's absorbed. So it starts to accumulate.
Where does it build up?
Especially in the liver. But the most devastating target is the brain. It's this slow, silent buildup inside the body that directly attacks the nervous system.
And the consequences of that buildup in the brain?
Well, the main consequence is this specific and often debilitating neurological disorder. It's called Manganism.
Manganism.
And what's quite striking, medically speaking, is how the M&M seems to interfere. Studies suggest it can sort of confuse the brain. It mimics other essential metals, maybe iron or calcium, and disrupts critical signals between nerve cells.
That neurological interference, that's what causes the symptoms that sound familiar.
Precisely. Manganism often presents with symptoms that are strikingly similar to Parkinson's disease. You see severe tremors, muscle stiffness, significantly reduced control over movement. And the research, tragically, confirms that concern. Yes, MU can cross the placenta if the mother has elevated levels in her blood.
Which is just terrifying.
Yeah.
Because unborn babies, very young children, they must be the most vulnerable.
They absolutely are, the most vulnerable demographic.
Why is that? Why are they so much more susceptible than, say, an adult worker?
It really comes down to protection. Or the lack of it. An adult body has what we call the blood-brain barrier. It's like a critical filter designed to keep harmful stuff circulating in the blood out of the brain.
Okay.
But in infants and very young children, that barrier, it just isn't fully developed yet. It's still forming.
So things can get through more easily.
Much more easily. While it's developing, the brain and the whole nervous system are just far more vulnerable. Substances like manganese can pass more directly into the neural tissue, potentially causing permanent damage during critical developmental stages.
And here's where it gets, well, even more complex, right? Because the exposure pathway wasn't always direct, even for the family.
Yeah.
Our sources talk about this concept of take-home exposure.
Ah, yes. This was the sort of silent, insidious reality of, well, older industrial life before stricter regulations.
So it wasn't just the worker breathing it in at the plant.
No. Think about that factory floor. Fine metal dust, just coating everything, settling deep into a worker's uniform, their boots, their hair.
And then they just wear that home.
Exactly. You can imagine maybe the wife handles that heavy, dusty work coat, shakes it out, perhaps, maybe on the porch, maybe even inside, before washing it.
Oh, wow.
That simple action would aerosolize these tiny particles of heavy metal dust, manganese, yes, but often lead, cadmium too,
Huh?
spreading them through the living space.
So they'd settle on furniture, floors, just in the air the family was breathing.
So spouses, children, they were being inadvertently exposed
Yeah.
over years, just inhaling or maybe absorbing these heavy metals simply by living in the same house.
And this was documented, right? This pathway. Until rules came in about changing clothes, showering at work.
Absolutely. Historical studies showed it quite clearly. The person doing the laundry, often the wife, was exposed. Children playing on the floor were exposed. It was a known tragic pathway.
And crucially, this contamination, it doesn't just stay put around the factory, does it? It moves.
Correct. The pollution is mobile. The sources confirm that, traffic, heavy machinery, even just strong winds around these industrial areas, they kick that fine MN dust back up into the air repeatedly.
Resuspension.
Exactly. And the wind can then carry it, sometimes for kilometers, settling in people's gardens, the soil nearby, eventually getting into the water table too.
Which leads us perfectly to the next stage, the environmental impact. The fjord itself is like this long-term archive holding the evidence of this industrial past. How did the waste actually get into the fjord water?
Well, over decades, the factory's waste laden with M compounds, iron dust, maybe oil products too, it seeped into the soil, then into the groundwater.
And groundwater flows, eventually reaching the fjord.
Precisely. That polluted groundwater migrated, carrying the contaminants with it, down into the fjord system.
And it wasn't just the metals causing problems in the water, was it? The sources mentioned a kind of cocktail effect.
A very nasty cocktail, yes. You had the metals, like Mn, potentially affecting the nervous systems of aquatic life. But at the same time, the fjord was often receiving excessive nitrogen, mainly from agricultural runoff nearby.
So a double whammy.
Pretty much. It created this compounding stress. The nitrogen leads to oxygen depletion, horrible algal blooms, while the metals are still settling in. The fjord ecosystem just didn't have much chance to recover.
And manganese, being a heavy metal, it doesn't just wash away, right? It sinks.
It sinks, yes. And it tends to bind very tightly to the sediment on the fjord floor.
So how do we measure the impact of that today, long after the factory's gone?
We look at the things living down there, the residents of the fjord floor, filter feeders, especially things like mussels and certain types of worms that live in the sediment. They constantly process the water and the sediment.
And they absorb the manganese?
They do. They effectively absorb and accumulate it in their tissues. This makes them a really crucial indicator, a sort of mirror reflecting the pollution levels, both the historical contamination and any ongoing seepage from the groundwater.
And that risk, it doesn't just stop with the mussels and worms, does it? It moves up the food chain.
Absolutely. That's the pathway. The metals don't disappear. They just change location, get concentrated in these organisms.
So people eating local shellfish,
Right.
even today.
Should still be gradually accumulating Mn, yes, if they eat them regularly. Years after the factory closed, the pollution is sort of contained down there, but it's still active in that biological cycle.
Which brings us, thankfully, towards solutions, towards the future. This is where Kesser and Steen come back in. They saw this huge, complex problem and focused on remediation. How do we stabilize this land? How do we manage this toxic legacy safely?
Right. And traditionally, cleaning up heavy metal contamination involves either very high-tech approaches or, massive amounts of labor. Digging things up.
Like wastewater treatment.
Modern wastewater treatment, yeah. It can remove heavy metals, but the problem is it concentrates them into sludge, which then needs to be dealt with.
And the other high-tech option, resource recovery.
Yes, internationally, experts are definitely exploring resource recovery, trying to extract valuable elements back out of waste streams like incinerated sludge ash.
Why is that so important? Getting metals out of ash.
Well, it's not just about getting rid of the toxic stuff. It's also about scarcity. Some of these elements, phosphorus, zinc, even manganese, are valuable and increasingly scarce resources. We need them for modern manufacturing, fertilizers, batteries, all sorts of things.
So recovery solves two problems, waste and scarcity.
Potentially, yes. But these methods, they tend to be expensive, complex to implement on a large scale.
Okay. So what's fascinating here, what Kesser and Steen were looking at, was this quite different approach, more nature-based, lower tech maybe, using an ecological cover, they called it, like a wild green zone.
Exactly. Using it as a natural filter and barrier.
Yeah.
It's really quite an elegant idea leveraging nature itself as a form of green technology.
How does that actually work? How can plants stop heavy metal pollution?
It seems to work through made of three main ways. First, there's the simple physical barrier. Trees, shrubs, they act like giant passive nets. They catch wind-blown metal dust on their leaves and branches.
So it just stops it blowing further inland or people breathing it?
Pretty much, yeah. Reduces the spread. Second, there's stabilization. When those leaves and branches eventually fall to the ground, the metals that were caught on them bind to the organic matter as it decomposes.
Ah, so they become part of the soil layer.
Right, a stable, relatively immobile soil layer. It effectively locks the contamination down in place.
Okay, barrier, stabilization,
Mm-hmm.
and the third mechanism. You mentioned roots. That sounded almost like biological magic.
Well, it kind of is. It involves the root networks, definitely.
Sure.
But also, crucially, the associated fungi, the mycorrhiza.
Mycorrhiza. That's the underground fungal network.
That's the one. It's vast, mostly invisible, and acts like this huge extended web for the plant's roots. Together, the roots and this fungal network dramatically increase the soil's ability to bind onto stuff.
And they bind the heavy metals?
They help bind and encapsulate them, yes. Metals like manganese, copper, lead, they get locked into chemically insoluble forms within the soil structure.
Insoluble, meaning they can't dissolve in water easily.
Exactly. So if they're insoluble, they're far less likely to dissolve when it rains, leach down into the groundwater, or get washed into the fjord. The green zone effectively acts like a permanent natural containment system, a vault, as you put it.
That really is the takeaway, isn't it? It's practical, it's sustainable, maybe less disruptive than trying to dig up and move huge amounts of contaminated soil, which itself carries risks, like kicking up more dust.
It allows the ecosystem itself to do the heavy lifting of containment and stabilization over time.
So let's recap then. We've journeyed from this essential element, manganese, to its toxic impact through industrial exposure. The hidden danger of take-home exposure affecting families.
Right, how that pollution persists, archived in the fjord sediment, still cycling through the food chain.
And then this innovative potential Kesser and Steen highlighted, using nature itself, these green zones, to potentially remediate our industrial past.
And if we connect all that to the bigger picture, I mean, the core theme running through this, ethically, financially, it's really about justice between generations, isn't it?
How so?
Well, factories' operations, its legacy, it created these huge health and environmental debts. Debts that are still affecting the environment and the health of people who, frankly, weren't even born when the worst of the pollution was happening.
That debt gets passed down through the sediment, the food chain.
Exactly. It's transferred, which is a powerful way to think about environmental cleanup, I think.
It really is.
So here's a final thought, maybe for you listening. Given that these heavy metals, like manganese, they don't just vanish, right? They only move around, change form. What ethical responsibility do we have now? Especially with emerging resource recovery technologies, the high-tech stuff Kesser and Steen also looked at. Should the focus shift beyond just containing the waste? Should we be pushing harder for secure, safe reuse and cycling of these metals?
So turning a toxic liability potentially back into a resource.
Maybe. If we can find ways to make the recovery cost-effective, truly safe, perhaps we could solve two massive problems at once, cleaning up the legacy waste and addressing resource scarcity. That feels like a key question for responsible resource management moving forward.
Welcome to the Deep Dive.